I have two models. Which one should I choose? The model on the left is a quadratic model or a response surface model. So it contains main effects, two-factor interactions, and quadratic terms. The model on the right is a linear model, so it just contains the main effects. The question I want to ask is which model should I select? Now, the answer actually, I'm not going to select either model. Model building, in my view, is part science and part art. And I want to share with you the thought process of selecting models. Let me focus, first of all, on the R-squared statistic. And you can see, well, if you go to 3 decimal places, you're at 0.994 versus 0.987. If you're at 2 decimal places, they both have an R-squared of 0.99. Well, okay, you want R-squared to be as high as possible, but it always gets larger as you add complexity. So the adjusted R-squared is intended to penalize complexity. So let's look at the adjusted R-squared. We have 0.984 on the left-hand side versus 0.983 on the right-hand side. So they're pretty much the same figure. The other consideration is possibly the difference between R-squared and adjusted R-squared. So that difference is slightly bigger on the left-hand side versus the right-hand side. And you want the difference to be as small as possible. But, you know, you're having to work to the 3rd decimal place on those statistics to get anything meaningful. And one of the things I want to get across is the R-squared is something we're often drawn to. It's not a very convenient statistic for model comparison. So let's look at some other things that we can think about. Well, the method of least squares is aimed at, well, by definition, it minimizes the sum of squares associated with the error term, which appears in this analysis of variance. But the nature of the method is such that you're always going to try and draw a line that goes through the data points. And therefore, there's a bit of a bias almost towards the data that's used to build the model. And so if we're thinking about using a model in terms of making predictions, it would help if we could reduce that bias. And you can do that through a process of cross-validation. Now, I'm not going to go through the formal method of cross-validation using JUMP, but there is a statistic that uses cross-validation in its derivation, and that is the PRESS statistic. So let me turn PRESS statistic on for both of these models. And what this does is to compute the error sum of squares, but based on it uses a method of cross-validation where you leave one data point out and then you build a model without that data point in, and then you ask how well that model predicts that data point. And so we have this PRESS error sum of squares, which is a more reliable indicator in many ways. And so you want to minimize the PRESS error sum of squares, which is 39 on the left-hand side versus 19 on the right-hand side. So based on that statistic, you can see much. I guess one of the points I want to make out is if you try and compare adjusted R-squared, you have to go to 3 or 4 decimal places. It gets crazy. But here you've got a distinction between 39 and 19. You can clearly see 19 is smaller than 39. That's indicating the model on the right-hand side is doing a better job for us. And that's reflected in the R-squared of 0.97 versus 0.94, 0.95. Okay, so should we therefore, well, based on the PRESS statistic alone, you'd go for the model on the right-hand side. I'm going to introduce a more modern statistic, which is designed for model comparison, and isn't specific to the least squares method. It can be applied across a very broad class of model types, and that statistic is the AIC. This will get added to the summary of fit reports. And what we want to achieve with AIC is we want to minimize the AIC. So on the left, we have 134 versus 53. Again, notice a very big difference. If I want to compare models, much easier to do it with the AIC than it is with something like an adjusted R-squared. It's very clear. 53 is much smaller than 134. So I've got a couple of statistics now which are pointing to the model on the right hand side. Does that mean I should select the model on the right hand side? Well, no, I think there's a couple of things that we can do. We could ask the question, now AIC is a statistic which penalizes complexity. So what we're really saying is the model on the left hand side, because it has a high AIC, is too complex. The adjusted R-squared is supposed to penalize complexity, but you can see this adjusted R-squared isn't really helping us too much. So the AIC does a much better job at telling us that relative to the model on the right-hand side, we have too much complexity. So rather than just take the model on the right-hand side, I'm going to take the model on the left, and I'm going to reduce the complexity of the model. In essence, what I want to do is try and minimize the AIC by removing unnecessary complexity. Now I can, and I will use the p-values ultimately to make that decision, but I don't want you to think that you should just blindly follow p-values. Let's just understand what's going on with a p-value. And the best way is to just understand what this model looks like. So this model is a model which contains quadratic terms, which means I'm describing curvature in these data. Look at the height. This is a straight line. There's no curvature in the data. So my model is describing curvature, which I don't need for these data. So it makes sense to remove that curvature term for the height. And if I adjust the value of the height, I'm going to focus on the shape of these two curves. If the shape doesn't change, if the slope doesn't change, there's no interaction. And so I'm not seeing any interaction effect associated with height. So all of the second order terms in relation to height are unnecessary for this model. I have unnecessary complexity. So I'm going to remove those. And in fact, the recommend, well, I wouldn't say recommended, but the term with the worst p-value is the quadratic term for height. And we have an interaction involving height. I've also got a quadratic term for the thickness. Maybe I'll leave that for now, because maybe I'm just having this discussion about the height terms. Or maybe I'll stop here. Let's just look at the thickness. It's the same arguments. This is a straight line. There's no curvature at all for thickness, so that can go. And the interaction with the height we've already discussed. Thickness versus width. Let's look at that one. So the thickness and width. If I change the value of the width, does this slope change for the thickness? But no, it doesn't. So that's why these terms are they're not statistically significant, because there's no effect. We're not observing this effect within the data. So we don't need to describe it within the model. And now I'm left with just statistically significant terms, and I have a quadratic term for width squared. So let me just double check this. And there is it's a subtle effect, but there is an effect, a slight curvature for the width. Now let's look at what's happened to the AIC. I'm now down to 52, whereas before what I had was I had 134 originally, so it's come all the way down to 52. In fact, it's smaller than 53 now, so it's doing better than the model on the right hand side. I have to be a little bit careful with the phrase "it's doing better." When we compare AIC values, a difference of 2 units, you wouldn't really consider that to be statistically significant. So the model on the left and the right are pretty similar. But this term is statistically significant. I would really want to apply some scientific or engineering judgment about the curvature of this. But let's also look at the press. So the press here, the error sum of squares is 13 versus 19. And because of that, the associated R squared is 0.98 versus 0.97. So the press statistics are better for the model on the left-hand side. So should I take the model on the left? Well, at this stage, I wouldn't. I'd now focus on the model on the right-hand side. And so let's just understand this model and look to see whether I should take this model, because it's a simpler model. And if I have a choice between a complex model and a simpler model, I would like a simple one. Let me look at this section on lack of fit. There is some lack of fit associated with this model. And I'm going to interrogate that lack of fit by saving the residuals. And you can do some residual diagnostics in the platform, but not the type of diagnostics that I prefer to use. So what I want to do is to save my residuals and then come to the data table and create a graph of those residuals. But I want to plot them versus the x's. So I'm going to plot them versus the thickness first of all. And let me put a reference line on here at 0. It just makes it easier to look at this. And what you'll see there is that there is a very slight piece of curvature. In fact, in order just to make this easy, I'm going to come to the column switcher and put, instead of thickness, let's put all of the x's here. And now I can do this. Okay, so this is looking at the residuals versus thickness. There's a little bit of curvature, but it's a tiny piece of curvature. Let's look at width. Wow, that's a much bigger piece of curvature. And then there's height, no curvature at all. So if I had to do one thing to refine my model, it would be to address this curvature that I see with respect to the width. Now, this curvature could be because I'm missing a quadratic term for width, or it could be any other second order effect. So what I want to do is to consider all of the second order effects associated with the width. So if I come back now to this model and I can edit the specification for this model and look at the width versus these three, and I'm going to cross those. So that's going to give me the quadratic term for the width, but also the two-factor interactions. Now you can see, if I look at the AIC, it's 52 versus 66. So what I've done, I've not done a good job here. I've added complexity, and that complexity is being penalized. It's over complex. But now let me just refine the model by taking out the terms that are not statistically significant. That's taken me down to 57, still not as good as the 52. And then I remove this, and now I'm at the same model as on the right hand side. And this is the point I stop. I no longer have to choose, do I have the model on the left or do I have the model on the right? Well, they're the same model now, and that makes my life so much easier. And what I would say, certainly my certain style of model building, is to say, let's take a complex model and simplify it. Let's take a simple model and add complexity, and let's see where they meet in the middle. And they have met in the middle. We've used different techniques, different rationales for the two different models, but we have come up with a consistent endpoint for both of those journeys of model building. I hope you found this video helpful. If you did, then please give it a like. Thanks for watching. Bye for now.